All right, we're on number 6 now. You should know the difference between periods and families or groups. Remember that a period is this here. A period goes across like this, a family or a group. A family or group is going to come up or down. Up and down just like that. So everything inside of a family or a group is going to have the same physical and chemical characteristics. Here we have the alkaline metals again. These are the alkaline metals. The alkaline earth metals are these right here, but it doesn't have to be in a named group. Anything in the same column or same group is going to have the same physical or chemical characteristics. So one more time for number 6, across the periodic table like that, that's a period. If we move across like that, that's a period. Up and down, we call that a family or a group. Up and down, we call that a family or group. That's number 6. Number 7 says you should know periodic trends for the following characteristics. Let's start with atomic radius size. Remember that atomic radius size gets bigger as you move from top to bottom. Let's go back to this slide right here. As you move from top to bottom, atomic radius size gets bigger. As you move from left to right, atomic radius size gets smaller. That's not exactly intuitive. Remember, atomic number gets bigger as you move from left to right, but atomic radius size gets smaller as you move from left to right. Atomic radius size gets bigger. That's going to mean that the biggest atoms are going to be in the lower left-hand corner of the periodic table, and the very smallest ones are going to be right here on the upper right-hand corner of the periodic table. Let's talk again in number 7 about ionization energy. Remember, the ionization energy is the energy required to remove an electron from the outermost shell. Ionization energy increases in this way. Let's move up to that slide. Ionization energy is going to increase as you move from lower left to upper right. Or if you want to break that down, if you move from the lowest part of the periodic table up, ionization energy increases. Ionization energy increases this way as well. So the ionization energy is going to be low down here, about 376 kilocalories per mole for atoms down here. And then if you move to the upper right-hand corner, about 2,081 kilocalories per mole in the upper right-hand corner. So ionization energies increase as you move from lower left to upper right. That's the trend. Then we talked about electron affinity. For our purposes, we're going to consider electron affinity and ionization energy to be the same. At least the trend is the same. As you move from lower left to upper right, electronegativity, ionization energy, electronegativities, electron affinity, electronegativity, and ionization energy all increase as we move from lower left to upper right. So that's number 7. Number 8. Number 8 asks us to distinguish between the total number of electrons which an atom possesses and the number of valence electrons. You should know how to determine the number of valence electrons for a given atom from its position on the periodic table. Let's move this way. So I'll turn the light on now so we can get a better look at the periodic table. So remember that the total number of valence electrons is given to us by this number right here. Aluminum has 13, chlorine 17, bromine 35. The number of electrons, the number of protons for a neutral atom are going to be the same. But if we want to know the number of valence electrons, we look up here at the group number. So everything in this first column has one valence electron. In other words, one electron in its outermost shell. Everything here, 2 electrons in its outermost shell. If we move across the transition metals, we come to boron. This group here is going to have 3 valence electrons, 4 valence electrons in its outer shell, 5, 6, 7. We're going to say that the noble gases have 8 valence electrons. So there was some discussion in class about whether it should be 0 or 8. 0, the people that argued 0 said that there were no electrons to be shared, but we're going to say that the noble gases have 8 valence electrons. So one more time. The number of electrons that an atom has is determined by the periodic or the atomic number. Copper has 29, zinc 30, or whatever it is. The point is that the atomic number and the number of electrons are going to be the same. But if you want to know valence electrons, just look to the group number. 1, group number 1 will have 1 valence electron. Group number 2, 2 valence electrons. Let's jump over here to boron. 3, 4, 5 valence electrons. The nitrogen group, oxygen group has 6, 7 for the fluorine group or the halogens, and the noble gases have 8 valence electrons. 8 valence electrons. So that takes us to number 8, through number 8. Let's look at number 9. What is meant by the term shielding and what does it help to explain? Here's what it helps to explain. As we move from left to right on the periodic table, as we move from left to right, the atomic radius size decreases. But when we move from top to bottom, the atomic radius size increases. We looked at the atomic radius size trend increasing as we went from top to bottom. So what's going to happen is that as we move from top to bottom, atomic radius size increases for a couple of different reasons. One of the reasons is because of the fact that as we move from top to bottom, we're moving into higher and higher and higher main energy levels. So for example, hydrogen here is in the 1s, or the n equal 1, or the first main energy level. As I move from this level to this level, I'm moving to main energy level 2, main energy level 3, and so forth. In other words, the electrons are moving into higher and higher and higher energy levels. That's one explanation for why atoms get bigger and bigger and bigger. But it's not the whole story. The whole story is that as you move down from top to bottom, what's happening is that there are more and more and more intervening electrons. There are more and more and more electrons that are coming between the nucleus and the outermost electrons. So lithium, for example, has a total of 3 electrons, but one of them is the valence electron. That one on the outermost shell is feeling some type of shielding effect by the 2 electrons that are between the nucleus and that outermost electron. But that effect is going to be magnified again and again and again as you move further and further and further out. So shielding is that this effect of the attractive force of the electrons on the very outside being mitigated or lessened by intervening electrons that are closer and closer and closer to the nucleus. It's decreasing the nuclear charge as you move further and further and further out. That's shielding. We're now at number 10. You should know where the metals in are located on the periodic table and where are the nonmetals. That's a pretty simple question. So metals are located to the left of the zigzag line. They're things that you traditionally associated with being metals, things like nickel, copper, zinc, gold, silver, cadmium, all mercury, all those you consider in your everyday lives. You've encountered those, and those are certainly metals. So everything to the zigzag line, to the left of the zigzag line, including the F block, including the intertransition metals, but not including hydrogen. Hydrogen should be really on this side of the periodic table with regard to whether it's metallic or not. It's really a non-metal, so it should be on this side. The zigzag line right here divides the metals into non-metals. Everything to the left of the zigzag line, with the exception of aluminum and polonium. Those two, aluminum and polonium, are non-metals. Or excuse me, yes, aluminum and polonium are metals. Everything on the zigzag line are metalloids. So boron, silicon, germanium, arsenic, antimony, tellurium, and astatine, all those are metalloids. Everything to the right of the zigzag line is a non-metal. So that takes us through number 10. And so on the next video, we'll take care of 11 through 15. Thank you.